What we're going to look at today is the idea of connecting angular acceleration directly to torque. So the other day we talked about angular acceleration itself, and now what we want to try to do is to connect that angular acceleration idea directly to the idea of torque, and we'll see how those two things are related to each other, because of course I talked to you about twisting things, but not necessarily about how much angular acceleration you get out of something when you apply a particular torque. So let's consider a ball on a string that's being rotated, maybe the mass M are from the center of some kind of a circle, and that you apply some force to it that's tangential to the circle like this, okay? And what I showed you on Thursday is that torque is equal to the distance from the axis of rotation times the amount of applied force. What we're trying to do today, our goal is to equate or get a relationship between torque and alpha. So we want to try to figure out how to get an alpha in over there on the right side of that equation. And so to do that, what I want you to tell me, and you can press your space bar to answer this and just talk, or if you're unmuted, you can just do that, is what is this thing? What is force? What has force always been?
Mass times acceleration.
Yep, mass times acceleration. Okay, so in this case, if we're thinking of force as being equal to mass times acceleration, what sort of acceleration are we thinking about here in this position? If we're looking at this area right over here where that mass is being pushed upon by a force, when we say acceleration, are we talking about centripetal acceleration? Is that what we're talking about there? What do you think?
I think it would be tangential.
Tangential acceleration, good. So what we're really thinking about here is a tan, okay? So let's continue exploring this idea of it being a tan. All right, so it's kind of recursive branching thing here we have. A tan. So what does a tan mean? What does it mean? Not how we calculate it, but what does it mean?
Like how much force you needed to turn it.
Okay, how much force you need to turn it. That sort of, but when we thought about acentripetal, wasn't that what we were talking about? Is that that's really how much force is needed to divert something off of a straight path? What is a tangential acceleration doing though?
Is that the acceleration when it's like if it weren't connected to that middle piece, if there weren't centripetal force?
Okay, so keep digging into that, Emma. So if it is, no, you're all right. So if it weren't connected to that, what would it mean would happen to the particle? Lindsay, did you have something?
I was just gonna say, like, the tangential acceleration like speeds up or like slows down the curve.
Yeah, it's going to speed you up or slow you down. And so a tangent, the way we were calculating that was by multiplying r times alpha. Okay, so if I go back up here and I kind of follow through this whole line of thinking and substitution, what I can now say is that torque is equal to r times force, which we said was mass, times a tan. But then we just also said that a tan is r times alpha. It's how much we speed up or slow down the spinning thing. So it's mass times r times alpha. And then look, what if we regroup terms, we get something new. We get that torque can be expressed as, I'm just rearranging in a particular way here, mr squared times alpha. All right, I'm going to put a little box around that because we're going to think about this equation a little bit and what it implies. Torque equals mr squared times alpha. There's a little bit of symmetry here in the rotational case to what is going on in the linear case. In the linear case, in the linear world, we said F equals m times a. Here in our rotational world, we're saying torque, which is a force-like thing, is equal to something times alpha. So in each of these cases, we have a force-like thing on the left side, we have an acceleration-like thing on the right side, and then something else that's a multiplier, okay? So in the original linear equation, we have mass over here. What is mass? What is it? What does it measure for an object? This is a little bit of a kind of obscure question, but we're digging back to when we first began thinking about force. It measures a property of something, property of matter. Let's say you have two objects. One has very little mass and one has a lot of mass.
Density.
Okay, her density. If we think about pushing on something of low mass versus pushing on something of high mass, what would be the difference if I apply equal forces? If I apply the same force to a low mass object that I do to a high mass object, linearly.
Faster acceleration. Sorry.
Okay, different accelerations, right? Remember when I was throwing apples at the classroom door and all of that sort of thing? So different amounts of acceleration occur if you apply the same force to equal masses. This has to do with the inertia of the object. What's inertia? You can just volunteer by pressing, you know, just talk. What is inertia?
It's like the law of Newton that says that like objects in motion stay in motion unless acted on by an outside force.
Okay, objects in motion will continue doing what they're already doing in the linear space. So here in this new equation, we have this thing right here. It's a bundle, mr squared. And the name of it is actually the moment of inertia. It measures the rotational inertia of an object. And it is usually represented by the letter I, capital I. Well, what do you suppose the moment of inertia is measuring if you're thinking about this equation as being parallel to the other equation? What does the moment of inertia tell us about an object? It's going to function the same as mass in the other equation. Any guesses? Roxy, go ahead.
Like how much acceleration is needed to move it? Like if mass dictates how much acceleration is needed to move it, then
Okay, so very close. So what you're thinking about is it's really, go ahead, Lindsay.
Or just maybe the effect like the acceleration is going to have on that spinning object.
Okay, right, but let's think about, instead of the acceleration, in both cases, the torque, right? The twisting force. If you apply a certain amount of twisting force, how much acceleration you will get out of it. Or another way to think about it is how resistant an object is to rotating. So I want to switch over here and share with you a short video we're going to watch together. It's a really cute demo that a dad did with his kids. He's a physics teacher. And I'm going to share this little YouTube. Let's see, sharing, where he changes the moment of inertia of an object. Uh-oh, I think we're going to have to watch an ad first, though. Hopefully it's a decent
The
ad.
coronavirus. We have it totally under control.
Sorry.
Okay, hi, this is Rhett, and I have two girls here. They're going to help me with a demo on moment of inertia. What do you think about that?
Cool.
So, which of you two girls is stronger?
Me.
Are you sure?
Mm-hmm.
Okay.
I'm really
We're going to do a thing. I put these together already. Okay, here I have two sticks. This one's got two juice boxes on the end of the stick. Same two juice boxes in the middle. So, can you girls tell me which one you think is heavier?
Okay, that one.
Why do you think this one's heavier?
Because they're both in the middle of, both put together make heavier weight.
You think so? What about you?
I think they're the same.
They're the same? Why do you think they're the same?
Because
They're both light.
They're both a stick, and they both have 2 juice boxes. So they're both the same stuff, right? So they're the same.
Yes.
So what we're going to do is we're going to play a game to see who's stronger. And what you're going to do is you're going to take the stick and hold the middle, and we're going to see you can turn it back and forth 10 times as quick as you can with just one hand. Does that sound like a fun game? Okay, you hold that one in the middle with one hand. One hand.
Oh,
you hold that one in the middle with one hand.
Light.
Okay, on your and you're going to one-handed. It's going to be 10 times this way. 1, 2, 3, 4, like that. On your mark, get set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. She won.
I did 10.
No, you didn't do 10. You didn't do as fast.
I won.
Okay, now switch. Now hold in the middle. Okay, let's do it again. On your mark, get set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So which one's easier?
This one. That one.
Okay, so
I
this.
couldn't do it because my wrist hurt red.
But you did a really good job. So this is an example of two things with the same mass, but different mass distribution. This one has masses at the ends, and this one has masses closer in. So this one's harder.
Okay, so explain what you just saw there. Somebody want to recap that demo and explain what happened in there? Anybody?
Well, they increased the radius, right? So it meant that they needed more torque to accelerate the object, even though it had the same mass.
Okay, so which one was harder to flip? Where the juice boxes were on the ends, right? So these are two objects of identical mass, but different moments of inertia. So moment of inertia has to do with mass distribution, not just mass itself. If we were together in the classroom, I would be doing this demo for you, but instead we're gonna invite a professor from MIT to do it. This is Walter Lewin. He's quite entertaining, but I have a series of things that I roll down ramps, and he will ask you to think about making predictions for which items, when rolling down the ramp, will win a race. In other words, we want to think about moment of inertia as resistance to rotation. Okay, so the higher the moment of inertia of a certain object is, the more it's going to resist rotating. Actually, before we look at that demo, let's look at page 210 in your textbook. So that's what I have here on my screen right now. Page 210 lists the different moments of inertia for objects of different shape, and in fact, flipping around different axes. So the top one, this is like a hula hoop. So the body of a person would be in the middle, that's the rotation axis. And you see that the moment of inertia for the hula hoop is just mr squared. Okay, it's mr squared, just like a ball on a string would be. But for other objects, like or I guess the same object tilted vertically, if you rotate it around a different axis, the moment of inertia is different. It's 1/2 mr squared plus 1/12 mw squared, where w is the width of the hoop. So you know, as you look down this column and you look at all these different moments of inertia, you may be wondering, how the heck did anybody calculate these? Well, this is done through calculus. What you do is you basically integrate from the center of the object. You take basically little blocks of mass, dm, and you integrate from the inside out over the three-dimensional surface. It's pretty terrible to do. It's a pain, but you know, those of you who love math might want to do that someday, and you can do it. But for us, for right now, here's a table of these things to think about. So if you're thinking about something like a door, for example, a door rotating on its end has this axis of rotation right here, length L, 1/3 ml squared, it's example G. Whereas something rotating around the center, this is rotating around the middle, the moment of inertia is 1/12 ml squared. Okay, so these have different moments of inertia. So keeping this in mind, what we're going to be thinking about is items of different shape, items of different mass distribution rolling down this ramp.
Here, a brass solid cylinder. And here I have an aluminum one with the same dimension, the same radius, and the same length. But this one is at least 5 times heavier than this one, maybe 4 times. And I'm going to do a race between them. I don't need this anymore, so I can remove that. The angle is not important. And now the question is, which one do you think will win the race? Which one will reach the end first? The heavy one? Or the light one? Or maybe they arrive at the same time?
What do you think, Lee?
I think the silver one, the heavier one, the heavier one.
And the heavy one will win, right?
Yeah.
That seems reasonable, because if you're heavy, you go a little faster, right? Okay, I'll give you the aluminum one on your side. Ready for that? 3, 2, 1, 0. No difference.
Dead heat.
No difference.
Why is that?
So we know that if the cylinders have the same length, the same radius, that...
I'm going to mute him and he's going to keep going. Why is it? You know why it is. Why do those two things of same mass reach the bottom at the same time?
Because the force of gravity is the same for everything.
Excellent. The force of gravity is the same for everything. If you drop things even of different masses, you know they're going to fall at the same rate. Here we're thinking about the roll. The rolling is just governed by what we said earlier in terms of moment of inertia. It's governed by the shape of the object. Okay, so we're going to move his video ahead a little bit. He's just taking two cylinders again. But what I want to show to you is when he takes two different shapes and rolls them down the hill.
That the length doesn't matter. Now comes the question. I have here brass. We already agreed that the material doesn't matter, right? Whatever the material is, that makes no difference. But now the radius is very, very small. So they're both solid. The fact that they have different materials, it's no problem. We have already demonstrated that doesn't matter. They have different lengths. We have already demonstrated that that doesn't matter. But now comes the issue, would it make a difference if the radius is so different as they are?
What do you think is going to happen here while he's setting it up? What do you think? Two different radii. We've already seen mass doesn't matter.
Well, we said that like the increased radius means that it's going to be harder to twist or have, like the torque is going to be.
Okay, other thoughts? Now you see, they both go at the same time. Why did that happen? How come they both went down at the same time? What is moment of inertia telling us about resistance to rotation? Okay, and those two objects have the same shape, so their mass is distributed in the same way. So they're both going to resist rotation in an equal way. What he's going to do now is show you what happens if a...
Now I have a last question for you. This is aluminum solid, and this is aluminum hollow. Now we're going to do a race with these two. Which one do you think will win the race?
I think the solid ones.
The solid one will win the race.
Yeah.
Do all of you think that?
I think because the weight, we've already shown the weight doesn't really matter.
Let's pause this and go back to our table. Okay. Whoops, wrong page. All right, so we want to look at a hollow cylinder versus a solid cylinder rotating about the center. So we can think of the hollow cylinder as this one. We can think about the solid cylinder as this one. Or I suppose, actually, let's think about our hollow cylinder as this, mr squared. So we're comparing mr squared to 1/2 mr squared, which has a bigger moment of inertia. Mr squared or 1/2 mr squared?
MR squared.
Mr squared, all right? This one is twice what this one is. So which one is going to resist rotating more?
The hollow one.
The hollow one. That's weird, right? Isn't it counterintuitive? All right, so let's watch. So what we're predicting here is that the hollow one is going to lose the race.
So it's whether there's any airflow comes into it, maybe because it's hollow. Could that affect it?
Well, what is your vote?
I would say the solid, yeah, solid. Intuition.
The solid one will win.
Yeah.
You will think? Same time.
I think
So we have 3 people for
same time, I think.
this one will win, and we have You also the same time?
Same time.
Two people, same time, 2-1. This one will win. 3, 2, 1, 0. The hollow one will always lose.
The hollow one will always lose. All right, so that's our demonstration of moment of inertia. So, oh, I see somebody has a chat here. So that is how torque is related to moment of inertia. So going back, last bit is just to think about if torque is equal to R times F and torque is equal to moment of inertia times alpha, that means we could also say that R times F equals I times alpha. And that gives us a real relationship between the twisting force applied and how much angular acceleration that you achieve.